In the last few lectures, we had looked at solving the diffusion equation, Laplace equation if there are no sources or sinks, or what is called a Poisson equation if there is a source within the domain. We first solved it in a Cartesian coordinate system for the heat conduction in a rectangular block as well as the flow in a rectangular channel. And then we were trying to solve it for a spherical coordinate system for the particular problem of the effective thermal conductivity of the composite. The composite consists of spherical inclusion of particles with thermal conductivity Kp in a matrix which has thermal conductivity Km. Okay. The direction in which the temperature difference is applied is designated the z direction, and the composite is of extent L in the z direction. The temperature difference is delta T, and we were looking for an average flux of the form QAV is equal to minus K effective into delta T by L in the z direction. We were trying to find out what is the effective conductivity as a function of the matrix conductivity Km and the particle conductivity Kp. So, that was the problem. As I had explained in the last lecture, when you put a particle in a matrix, if you did not have any particles, the heat flux lines would just be straight lines which would go from one surface to the other surface. The temperature would be have a linear variation. So, T will be equal to T naught plus T prime Z, where T prime is the temperature gradient. Where T prime is the temperature gradient, delta T by L, and Q Z will be equal to minus K into T prime in this case. When there is a particle, depending upon whether it is more or less conducting, the heat flux lines will either come preferentially through the particle or they will preferentially go around the particle. The former if the particle conductivity is greater than the matrix conductivity, and the latter when the particle is more insulating than the matrix. And because of this disturbance, there is going to be a disturbance to the heat flux, because there is a disturbance to the flux lines. And we were considering the dilute limit for very low volume fraction, where the disturbance to the temperature field around one particle does not affect the temperature field around another particle. So, each particle can be considered to be placed in a matrix in which the temperature is a linear function of z far from the particle, and there is a disturbance to the temperature close to the particle. So, each particle can be considered to be in a linear temperature gradient. And then we can find out the disturbance to the flux due to each particle, add it up and average over all the particles to find out what is the the change in the total flux, and from that find out what is the effective conductivity. So, that is what we had considered here. So, the problem is as follows at the single particle level. I have a particle whose location is at z is equal to zc. Z is equal to 0 we took from the bottom surface. And the particle location is at z is equal to zc. And it is in a linear temperature field far from the particle, so that if Tc is the temperature, the temperature in the matrix at the particle center is Tc, the temperature in the matrix at the particle center is Tc, then the temperature has a linear variation far from the particle. The temperature has a linear variation far from the particle of the form Tc plus T prime times Z. Now, the flux depends only upon the gradient in temperature. It does not depend upon the absolute temperature. Okay. So, if I calculate an average flux around this particle, that flux will depend only upon the gradient in the temperature. It will not depend upon the absolute temperature. So, for the purpose of calculating the flux, I can set this constant temperature T c to be equal to 0. Okay. I can set this constant temperature T c to be equal to 0. Okay. And the problem then becomes, I have a particle, okay, let me try to, okay, radius r, placed in a temperature field in which T is equal to T prime times Z for r going to infinity. Okay. Very far from the particle, you have a linear temperature field. Okay. Note that this is the Z coordinate, this is the Z coordinate. In a spherical coordinate system, this is the radial coordinate r. Okay. And the angle between these two is theta. Okay. You recall that we have a third angle that goes around the particle, that is phi, okay, yeah, in a spherical coordinate system. So, I am analyzing this in a spherical coordinate system with origin at the center of the particle. Okay. So, what are the boundary conditions at the surface of the particle? Okay. I have a particle with conductivity Kp, matrix with conductivity Km. Okay. At the surface, at r is equal to r, okay, you require that the temperature in the particle is equal to the temperature in the matrix. Okay. The temperature at a point on the surface has to be the same whether it is in the particle or in the matrix. Okay. And the flux perpendicular to the surface has to be the same in both the particle and the matrix. Okay. The flux perpendicular to the surface Qr is equal to minus Kp partial Tp by partial r. Okay. Flux perpendicular to the surface in the particle at the surface has got to be equal to the flux perpendicular to the particle surface in the matrix. Okay. At r is equal to r. Okay. So, those are the two boundary conditions at the particle surface. The temperature has to be the same, okay, because at a point you cannot have different temperatures. Flux has to be the same. If the flux is not the same, then there will be accumulation of energy at a particular location. Okay. So, for a single particle, these are the two boundary conditions at the surface. There is a boundary condition at infinity, T is equal to T prime times Z. Okay. So, those are the boundary conditions at the surface and the boundary condition far from the particle. Note that the boundary conditions at the surface are what are called homogeneous. They just relate the temperatures in the particle and the matrix. Okay. They do not have any inhomogeneous term, okay, which would set a temperature, okay, at any location. That inhomogeneous term is actually in the limit as r goes to infinity. There is a condition that the temperature has to vary linearly with z, where this z is equal to r times cos theta, because the angle between z and r is cos theta. Okay. What are the temperature equations for the temperature in the particle and the matrix? Okay. Laplace equations, del square Tp is equal to 0, del square Tm is equal to 0, okay, in the particle and the matrix. So, we have to solve these two equations subject to boundary conditions. Okay, find the temperature field and then find the excess flux due to the presence of the particle, and from that determine what is the effective conductivity. Okay, so, that is the procedure that will be used. First things first, you can see that this configuration is symmetric about the z axis. Okay. Okay. There is a linear temperature field in the z direction. Okay. At a given z, there is no variation with x or y. Okay. that means that there is no variation in the meridional coordinate, the angle phi, around the axis. Okay. There is a variation in the r direction because you are applying boundary conditions at fixed r. There is a variation in the z direction, but z is equal to r cos theta. So, there is a variation in the z direction, which means that there is a dependence on theta as well. However, neither the conditions far from the surface nor the conditions at the surface depend upon the angle phi, and therefore, there is no dependence on the angle phi in this problem. It is symmetric about the z axis, and there is no dependence on the meridional coordinate phi. Okay. There is no dependence on the meridional coordinate phi. So, if I write this heat conduction equation in a spherical coordinate system, you recall we had derived this, okay, the Laplace equation in a spherical coordinate system, 1 by r square d by dr of r square partial t by partial r plus that was the Laplace equation in r theta phi spherical coordinate system. In this equation, there is no dependence upon phi, okay, and therefore, the equation reduces to 1 by r square d by dr of r square partial t by partial r plus 1 by r square sin theta that is the equation for the velocity field. Okay. Now, how do we solve this equation? Laplace equation, separation of variables. Okay. Express t is equal to f of r g of theta. Multiply the equation by r square, and if you multiply the equation by r square, these two terms will go away, and insert, substitute f times g and divide throughout by f times g. Okay. So, the equation I will get is 1 over f d by dr of r square partial f by partial r. Okay. In this case, they are total derivatives because f is only a function of r and g is only a function of theta. This is equal to 0. Okay. Substitute t is equal to f times g into the equation where f is only a function of r and g is only a function of theta. Divide both sides by f times g, okay, and this is the equation that you will get. In this, the first term is only a function of r, the second term is only a function of theta. Therefore, both of these have to be constants. What should the constants be? Okay, that we usually you recall in the case of Cartesian coordinate systems, we obtained that from the homogeneous boundary condition in one spatial coordinate. Since that the value of the variable had to be 0 on both boundaries, we got the solution in the form of sine or cosine functions in that particular direction. Okay, so, that is how we had solved it in a Cartesian coordinate system. What is it in a spherical coordinate system? Okay. Recall my spherical coordinates. R is the distance from the center, theta is the angle from the z coordinate. Okay. Theta is the angle from the z coordinate. Theta varies, as you recall, from 0 to pi. It is 0 on the positive z axis, it is pi on the negative z axis. Okay. So, the two boundaries in the theta direction are 0 and pi. However, there is no physical boundary in the theta direction, because both 0 and pi are within the material. Okay. So, there is no physical boundary in the theta direction. Okay. So, how do we get the boundary conditions in the theta direction? It turns out that the boundary conditions are obtained by using symmetry relations, and I will go through that in some detail in order to explain to you how these symmetry relations arise. Okay. And then after going through and getting the solution, we will then come back and we will start solving this problem in the r direction as well. Note that the inhomogeneous boundary condition is in the r direction as r goes to infinity. That is where you have applied a temperature gradient, and that is what is driving the temperature variations in the vicinity of the particle. Okay. So, you would expect homogeneous boundary conditions in the theta direction, but it is not obvious here because we do not have a boundary in the theta direction. So, let us examine this. Okay. 1 by g sin theta. Is equal to some coefficient, I will call that as minus alpha n. We will come back and find out what is this minus alpha n, okay, a little later. Okay. Normally, this equation is solved by defining a coordinate, okay, psi, which is equal to cos theta. Okay. Okay, there is a coordinate which is set equal to cos theta, and that implies that d psi is equal to minus sin theta d theta. Okay. So, d theta is equal to minus d psi by sin theta. Okay. If I substitute that into this equation, I will get 1 over g d by d psi of, okay, sin theta d theta is minus, okay, d by d psi. Okay. Then I have a sin theta here. And minus, okay, okay, for d theta I have substituted minus d psi by sin theta, okay, minus alpha n. Okay. And you can see that this reduces to 1 over g d by d psi of sin square theta dg by d psi. Okay. And sin square theta is 1 minus cos square theta. So, sin square theta is 1 minus cos square theta, and this 1 minus cos square theta is psi square. Okay. And the domain of this, okay, 0 less than or equal to theta less than or equal to pi, implies that minus 1 less than or equal to psi less than or equal to 1. Okay. So, psi varies from minus 1 when theta is equal to pi, psi is equal to minus 1, and when theta is equal to 0, psi is equal to plus 1. Okay. So, that is the equation, and okay, that is the equation in terms of psi. Okay. And I have to find out the solution for this. Okay. I can expand it out and write 1 minus psi square, okay, d square g by d psi square minus 2 psi dg by d psi plus alpha n is equal to alpha n g. Multiply throughout by g, okay, multiply throughout by g and expand out the derivative, okay, and this is what you will get. How do you solve this problem? Okay, the solution of this, okay, so I'll one way to solve this problem is to expand in a series, okay, g is equal to sigma, okay, p is equal to 0 to infinity a p psi power p, okay. Such a solution is always possible because psi is bounded between -1 and +1, okay. So, in the normal course you would expect this series to converge because psi magnitude is always less than 1. Okay. How do we find these coefficients? These are substituted back into the equation and then okay, solved for AP. Okay. So, I will just go through how this is done. Okay. Therefore, dg by d psi is equal to sigma just taking derivatives. Okay. Just taking derivatives. Okay. Note that in this first term here, okay, in this first term here, this is 0 for p equal to 0. So, I can take the summation just from p is equal to 1. Okay. Okay, because for p is equal to 0, it is equal to 0. Okay. Similarly, the second term is 0 for p is equal to 0 and p is equal to 1. So, this summation can be taken from p equals 2, okay, in this case, okay, because 0 and 1 the coefficient is 0. Okay. Substitute that into this equation. Okay. Substitute that into this equation. Okay. The first term is the second derivative. So, this is just equal to sigma p is equal to 2 to infinity of p into p minus 1 a p psi power p minus 2. Okay. Okay. Minus, okay, I have psi square times this. So, this is equal to sigma p is equal to 2 to infinity a p times psi power p, okay, minus 2 psi into dp by d psi, okay, okay, of p, this factor of 2 here, okay, there is a factor of 2 in this. Minus sigma of alpha n plus alpha n . So, the first term here is just summation p is equal to 2 to infinity of p to p minus 1 a p minus, I have here p into p minus 1 okay, p into p minus 1 plus 2p. Okay. So, p into p minus 1 plus 2p, you can verify this is equal to p square plus p, which will be equal to p into p plus 1. P into p plus 1 okay, plus sigma alpha n a p psi power p. Yeah. Okay. So, now in this first term here, I have psi power p minus 2 into a p into p into p minus 1. Okay. I can make the transformation p minus 2 going to p. Okay. I just renumber p minus 2 as p, which means that p becomes p plus 2, okay, which means that p becomes p plus 2. Okay. And the limit goes from 0 to infinity. Okay. The limit goes from 0 to infinity. Okay. So, therefore, I have when p is equal to 2, when I renumber it, I just get from 0 to infinity. Okay. Okay. I relabel p as p plus 2, that means that p is equal to p plus 2, p minus 1 is p plus 1, okay. A p plus 2 psi power p. Okay. Transform p minus 2 to p and p to p plus 2, okay, minus sigma, okay, okay, minus alpha n. Okay. Okay. Now, if I equate coefficients of equal powers of p, okay, if I equate coefficients of equal powers of p, okay, psi p, okay, I get a relation which effectively relates a p plus 2 to a p. Okay. If I say that coefficients of equal powers of p are equal, then I get a p plus 2 is equal to p into p plus 1, okay, minus alpha n by p plus 2 into p plus 1, okay, this whole thing into a p. So, if I know a p, then I can find out a p plus 2. If I know a p plus 2, I can find out a p plus 4, and if I know a p plus 4, I can find out a p plus 6. Okay. So, therefore, if I know just two coefficients, okay, if I know two coefficients a0 and a1, okay, then a2 etc., okay, can be calculated using this recurrence relation, and that gives me the solution of the equation. Okay. That gives me the series solution of this equation. Okay. So, once I know what is a0 and a1 for the psi power 0, the constant term, and psi power 1, then from that I can find out what is the coefficient of psi power 2, psi power 3 and so on. Okay. So, that is the way to find out the solution of this equation. Okay. So, there is the series solution for this equation. I should note here that this is called the Legendre equation. Okay. And these solutions are called the Legendre polynomials. The question that I had asked, what are the boundary conditions in the theta direction, okay, in order to get the eigenvalues and eigenfunctions for the theta coordinate, that has not yet been answered. I will continue that in the next lecture. I will see you then.